Okay, so we're into the last topic for this course, actually. Now, if you guys remember all the way back to the very first day of class, and if you can remember back that far, um, when I first started describing the idea of calculus, I said there were two different types of calculus: differential calculus and integral calculus. We've spent the majority of the semester talking about differential calculus and all of the things we can do with the derivative of a function and what it means. What we're looking at now and what we started looking at in the last couple of videos is integral calculus. All right, integration, or the process of taking an antiderivative. What I want to look at now is some of the meanings of that. Now, when we talked about the derivative, there were two meanings for the derivative, right? We had the idea of velocity, right? The rate of change of the position of an object, or the velocity of an object. And we had the maglev train as kind of our example. And then we got to talking about the rate of change of a particle moving along a defined curve. Essentially, the rate of change of the position of that particle along a defined curve, which gave us the slope of the tangent line to the curve. And there are two meanings to integral calculus as well. All right, we looked at one of those meanings at the beginning of one of the last videos that I did, and that is, again, going back to the idea of velocity and the relationship between position, velocity, and acceleration. You can move that relationship forward, position to velocity to acceleration using the derivative, and you can move that relationship backwards from acceleration to velocity to position using the antiderivative. Well, there's a second meaning for the antiderivative, and that is it is used to find the area of irregular objects. All right, so as far as we need to go with this in this course, it is finding the area under a curve. So, for example, if I have, let's say I have a curve that looks like this, and I have an A and I have a B, all right, I have an interval in X. Oh boy, this is going to be hard. Okay, let's see. And I have, all right, we'll pretend that hits A, and we'll probably have to pretend that actually does hit B. All right, and then we're looking at the area under here. All right, that's defined by straight sides, but top here that is defined by a function. All right, if this was linear, I'd have a rectangle and I'd have a formula. Or I'd have a trapezoid and I'd have a formula. Either way, I'd have a geometric formula, but I don't. All right, so there are ways to deal with this geometrically, and I actually want to use the book to look at this. So if we take a look at the book here, all right, we're going to use an actual curve, and just to see what this looks like, because the book can do it so much better than I can. All right, so I have the curve f of x, and I'm interested in finding the area of the region underneath that curve. Here, let's go here, between 0 and 1. All right, so one of the ways I can do that is by estimation. All right, if I split this region up into rectangles, all right, and I make, let's say, the midpoint of each of those rectangles hit the height of the curve, then I have a bunch of rectangles that I have a defined formula for, right? Base times height, base times height, base times height, and so on. Okay, so I can basically make an iterative formula by multiplying the base times the height for each rectangle and then adding those up. And what I get is an estimation of the area under the curve. Now, we saw from way back in chapter 2 when we talked about limits that if I can make that more precise by taking in this case, more rectangles. So the limit, it was getting closer to the point. But for this, if I take more rectangles, so if we go down here and we take a look, all right, with 8 rectangles, all right, notice I'm getting closer to filling in that area. I only have a few little empty spots there. With 16 rectangles, I've got even more of the area filled in and very little of that white space. All right, if I keep doing this and I keep increasing the number of rectangles from what the book got, starting with 4, then 8, then 16, 32, 64, 100, 200, you can start to see towards the end here what's happening with that first digit, right? 0.3, 0.33, 0.333, and so on, and it seems to be approaching 1/3. All right, so we could gather from this process that if we increased the number of rectangles infinitely, that we would have that whole area filled in and it would probably be 1/3. All right. Now, this is just the idea behind it. Okay. So we end up with this formula, and there's a reason I'm doing with this with the book and not writing it down, because this is just background material. You are not responsible to be able to repeat this. All right, so we can define the area under the graph as the limit as n, the number of rectangles, goes to infinity, of the sum of the area of all of those rectangles. Okay? And we get what's called the definite integral. So that is the definite integral. And we define the definite integral, this notation here, which we've already seen, but with boundary markers in. Notice here and here, the lower end of the interval and the upper end of the interval. All right, and that definite integral is defined to be the sum of the areas of all the little rectangles inside the curve. All right, so we need to worry a little bit about when a function's integrable, but that's also like worrying about when a function's differentiable. A function is going to be integral probably on its domain. Okay, it has to be continuous. Most functions are continuous on their domain with very few exceptions. And then the function is going to be integral as long as the integral is defined and exists. Okay. We're not going to be dealing with the geometric interpretation at all. All right, but the basic idea here is, again, you're looking at these rectangles with some point on the rectangle hitting the curve so that you have a defined height. All right. When we have a curve that exists above and below the x-axis, okay, we have to be a little bit careful if we're looking for the area under the curve, because the area above the curve is going to be positive and the area below the curve is going to be negative. And what's going to happen when you add that positive and negative is you have a subtractive process. All right, so you're not actually getting the area under the curve. So you'll see some definite integrals, if all you're asked for is the definite integral, might be 0, might be negative, all right, might not accurately represent the total area under the curve. When you're asked for the area under the curve, you have to kind of take into account what's above the axis and below the axis. All right, that's something you'll get more into in Calc 2, all right? But just be aware for right now, you would have to calculate actually 3 separate integrals. All right, so you would split here and you would split here, and you would do one antiderivative from A to this point here, one integral from this point to this point, and one integral from this point to B. And you would add R1 and R2, R1 and R3, and then R2 would be negative, so you would take the absolute value of that and then add it in. All right. Okay, so let's go back to the whiteboard here, and let's look at the process. All right, so the fundamental theorem of calculus is a thing. And what it says is, if I have the antiderivative from a to b of f of x dx, and I know that f, capital F, all right, so we're going to look at this. Capital F is an antiderivative of little f, right? That means that capital F prime of x equals f, like that. All right, then this antiderivative is capital F of b minus capital F of a. All right, now you may be wondering, where did my plus c's go, right? Because I get a plus c every time I do an antiderivative. All right, well, what happens is the plus c's cancel out, right? So if I do, let me just come over here, right? If I do this process and I say f of b plus c minus f of a plus c, all right, notice what happens here, right? I get f of b plus c minus f of a minus c, and the c's go away. All right, so we don't bother to write them when you have a definite integral. When you have an indefinite integral, what we've been doing, right, just a straight antiderivative, you have to put it in. All right, but they basically cancel out. You'll get a numeric answer is more or less where I'm going with that. All right, so let's just take a look at a couple of problems. Let's see, we can run through some basic antiderivatives here. So let me get some room. Got some room. All right, let's start with, because you should have had some practice by now doing basic antiderivatives. So let's start with, again, I'll run through the evens. All right, let's do this. The antiderivative from -1 to 0 of 4 minus x dx. All right, so here's what you're going to do. First step, you're going to take the antiderivative. All right, so forget about the bounds for a minute. Just take the antiderivative. So the antiderivative of 4x, minus the antiderivative of x. Remember, that's x to the 1, so we add 1 to the exponent, and we divide by that number. Now, instead of saying plus c, because I have bounds, I'm just going to make a little note here. These are my bounds. All right, so that's a difference in notation when we're dealing with a definite integral. All right, now I'm going to apply the fundamental theorem of calculus, which means basically I plug in. I take the top number and I plug it in. So I get 4 times 0 minus 0 squared over 2. All right, so there's the f of b minus, and then the f of a, I plug in the bottom number. 4 times -1 minus -1 squared over 2. All right, and now I have some arithmetic to do, and yes, this is almost always going to result in fractions. You're going to have to deal with that, or just go to decimal. Either way is fine with me. All right, so this is 0, and this is 0. Okay, so that whole first term there is 0. All right, so minus, I'm going to do this in steps here, 4 times -1, so that's -4. Minus 1 squared is 1, so that's -1/2. So let's see, -4 minus 1/2. If I put that over 2, that's 8, that's 9. So that's going to be -9/2 with another minus in front. So that's going to be 9/2 or 4.5. All right, and that is your answer. Your answer to these problems will be numbers. All right, all of your answers will be numeric. All right, let's see if I jump down a little further. Oh, just so you can follow along if you want to, I am on page 453 in the book, which is where your homework is going to come from. And that was... what was that? That was number 20. Okay. Let's see. How about we do number 24, because I know you guys love fractions and square roots so much. All right, so 24 is the antiderivative from 1 to 4 of the square root of u du. All right, so like with any problem that involves notation, before I do anything, I wish to rid myself of the notation, and I need to turn this into a power function. Whoop. I need to turn it into the correct power function. 1/2. Okay, du. All right, so same set of steps. Take the antiderivative. So I add 1 to 1/2, I get 3/2. So I get u to the 3/2 over 3/2. And that's being evaluated from 1 to 4. Now, I don't want to look at this. You shouldn't look at this with the complex fraction. So before I do anything, I'm going to bring that up, and that's going to be 2/3 u to the 3/2 from 1 to 4. All right, so I'm going to do my f of b. Remember, b is the top number first. So that's going to be 2/3 4 to the 3/2 minus f of a, that's the bottom number, 2/3 1 to the 3/2. I know there is a subset of the class who is going to want to just put that in their calculators. That's fine. I don't care. You can do that if you want. I'm going to work it out. All right, so we've got 2/3. So the 2 on the bottom here means the square root. So the square root of 4 is 2. And 2 to the 3rd power is 8. So that's going to be times 8 minus 1 to any power is just 1. So that's going to be 2/3. So that is going to be 16/3 minus 2/3. And look at that. We have a common denominator already. So 14/3, or its decimal equivalent. Give me just 1 second here because I forgot to mute my phone. Okay. Okay. Let's see what else can we do here. Do they have any that require a u substitution? I'm not seeing any. What about up here? No, I'm not actually seeing any that require a u substitution. All right, how about this? Let's do number 30. All right, so 30 is the antiderivative from 1 to 3. So the antiderivative from 1 to 3 of 2 over x dx. All right. Okay. Now remember, we can use the power rule as long as the power is not -1. This down here means I really have x to the -1 up here. All right, so when I have 2 over x or 2 times 1 over x, I have the natural log. So that's going to be ln, the absolute value of x, 1 to 3. All right, so I can plug in here, and I'm going to get 2 ln of 3. Well, the absolute value of 3 is just 3. Minus 2 times ln of the absolute value of 1 is just 1. I would say you could leave it like that, except ln of 1 is 0, and you should know that. So 2 ln of 3 would be sufficient as an answer there. You don't need to go to decimal for that. All right, now I'd like to point something out. I said back in the last video, or one of the last videos, that when you're taking the antiderivative of 1 over x, you have to put the absolute value signs around the log. This is why. All right, if we take a look at this function here, let me give myself some more room just to talk about the log function for a minute here. All right. Notice my bounds here were positive, so it wasn't an issue. I could have this, let's say, go from -3 to -2 of 2 over x dx. All right, so there's no issue with the function 2 over x being defined, right? 2 over x is defined because on this side, it basically just looks like this, right? And you're going to have -3, -2, so you get this nice area, right, all in there, okay? So there's no issue with that being defined. Once I take that antiderivative, though, I have a problem because the natural log is not defined there, right? Remember, the natural log, or any log for that matter, basically looks like this. It doesn't exist over here. So I can't plug these in unless I have that absolute value sign on my function, which is why we need it there. All right, so when I evaluate this one, I get 2 ln absolute value -2 minus 2 ln absolute value -3, which means I have 2 ln 2 minus 2 ln 3. And again, there's not a whole lot I can do with that other than put it in the calculator. All right, so this is why that absolute value sign is necessary, because the log function may not be defined on the same interval that the function you're taking the antiderivative is defined on. All right, I'm going to go for like 2 more. That'll bring the video to right around half an hour. And that should be, I'm going to just jump to a new page here. Okay. All right, so let's see. We had some questions on some of these from class the other day. So let's do number 34. All right, so 34 is the antiderivative from -1 to 1 of x squared minus 1 squared dx. Okay, now, this is one that you might look at and say, okay, I have a composite function. Can I do a u substitution? All right, you can try. All right, it won't work. Because if I try to do u substitution here, I would have to make u this, right? So I would have to say u is x squared minus 1, which would make du 2x dx. And right there is the problem. I do not have that extra x in there. All right, so that's not going to work. Right now, if I can't do a u substitution, I have no other choice than to multiply it out. All right, because all I have is the power rule. So -1 to 1. If I square this, right, so I would have to do x squared minus 1 times x squared minus 1. When I do that, I'm going to get x to the 4th minus 2x squared plus 1 dx. And now I can use the power rule on it. Okay, so x to the 4th, we add 1 to the exponent, that becomes x to the 5th over 5 minus 2, and then add 1 to the exponent, so that becomes x to the 3rd over 3 plus antiderivative of a constant is the constant times x, and then we're evaluating that from -1 to 1. All right. There's not really a whole lot for me to do here except to make that 2/3, which I'll do in a minute. All right, so plug in the top number. I'm going to get 1 to the 5th, So it's 1 over 5 minus 1 to the third. So that's going to be 2/3 plus 1 minus, and I'm going to put a parenthesis around what I'm subtracting, negative 1 to the fifth. Remember, odd exponents preserve the sign, so that is negative 1/5 minus negative 1 to the third is going to be negative 1, so that's going to make that a plus 2/3, and then plus a negative 1, which is going to be minus 1. And yes, we have a lot of fractions, and if you want to, you can just throw that into your calculator. That's going to be, let's see, 3 over 15. That's going to be 10 over 15. That's going to be 15 over 15. And then same thing here, minus minus, so that becomes plus. Minus plus, so that becomes minus. And then minus minus, so that becomes plus. All right, so let's see, we basically got the same thing here as we have here. So 3 minus 10 is minus 7. Minus 7 plus 15 is 8. This is also going to give me 8. So that is going to give me a total of 16 over 15. And that would be my answer. Okay. Keep in mind, when you're doing these, all of your rules for exponents and everything else, all of your rules for antiderivatives still apply, right? So power rule, log rule, E rule. And if you can't do a U substitution, then that means you have to simplify the algebra to turn it into the sum or difference of power functions. Now, there's another set of problems here that ask you specifically to find the area under the curve. Right? Now, remember I said there's a subtle difference between just evaluating the antiderivative and finding the area under the curve, right? Because if you're just evaluating the antiderivative, you're just doing the algebra. Finding the area under the curve, you need to worry about whether that area is above or below the x-axis. So I'm trying to see here. I think, which one do I want to do? I guess I will do, no, that's all above. Actually, it might not be an issue with any of these. I'm looking at these problems in the homework. All right, well, let's just do one of these just so you have a setup and you know what they look like. All right, this is actually the first set in the homework. I jumped to the second set, but let's do one of these. And I guess I'm just going to do number 6, 2, 4, no, that's all above. 0 and 4, that's all above. That's all above. That's all above. That's all above. All right, I'm just going to show you how to set it up. All right, so we don't have to worry about the above-below thing. I think they're saving that for Calc 2, is what they're doing. Okay, so let's do number 8, same page. All right, number 8 gives you this. F of x equals 4x minus x squared on the interval from 0 to 4, on the closed interval from 0 to 4. All right, now under normal circumstances, and I'm going to suggest you do this anyway, you're going to want to put this on your calculator or graph it by hand, either way, just to verify where your area lies. So for this one, you can put it on your calculator and you can see. All right, from 0 to 4, it's not a very good axis, but you get the idea. This function basically does that. All right, so this is the area that we're looking at. All right, so everything is above the x-axis. So there are no issues here. We can just take the antiderivative, right? So we do the antiderivative over the interval, so 0 to 4, 4x minus x squared dx. All right, so take the antiderivative first. So the antiderivative of this is going to be 4 times the antiderivative of x. So that's x to the first. You add 1 to the exponent and then divide by that number, minus add 1 to the exponent. So that's x to the third, divide by that number, evaluated from 0 to 4. All right, so I'm going to clean this up as I go. So 4x squared over 2. So 4 over 2 is 2. So that's going to be 2 times 4 squared minus 4 to the third over 3 minus, now we do the bottom. Put 0 in here. So that's going to be 2 times 0 minus 0 to the third over 3. All right, so this whole thing is 0. Over here, 4 squared is 16, and 16 times 2 is 32. 4 to the third, okay, so 4 times 4 is 16. 16 times 4 is, all right, so let's see, 6 times 4 is 24, and 240. Hang on, let me see. Because my brain is not functioning. Actually, I think I know what it is. 64. All right, so 64 over 3. So let's see, 32 times 3 would be 96. Minus 64 over 3, which is going to be 32. Over 3, and that would be your answer. By all means, just throw that into your calculator and get a decimal. I'm okay with that. All right, so I'm going to post this video and the homework assignment, and it's the end of the new material.